Good afternoon, ladies and gentlemen. This is OJB. I'm going to be talking to you here about indium antimonide nanowires. That is, and this is the fabrication and the analysis and the characterization and other things like that we do here in the at the Minnesota Nano Center, or things that I did there actually. And my principal investigator was Dr. Vlad Previag. The grad student I primarily worked with was Zedong here, and so these indium antimonide nanowires and these devices, they can be used for research in the quantum computing world, and they can also be used for fermion research. So those are some nice examples we have. And here on the right we can see an image of some images of hardware components and devices that are applicable with these nanowires. And so on the top right we can see one of the hardware components that's used by some quantum computers that are developed and sold by a company called D-Wave. And then on the bottom right we can see another spintronics device that operates on some ballistic conducting devices and ballistic conducting components, and as well as superconducting components. So we have that there, and so we can call these spintronics or flextronics, and these are just basically devices that can be modified with particular applied magnetic fields, and so we call them B sensitive. So it's sensitive to those magnetic fields, and we can do some special and nice things with that. All right, so here we have a special table. Now I don't mean to sound sarcastic here, but we have I'm going to highlight these two groups here, Group 3 and Group 5. Now these two groups here, we're going to also highlight what's green here, element number 49 and number 51. Now these are metalloids in particular, so basically metals that have semiconductor properties. Okay, so here we have some nice SEM images. On the right, we have a bundle of indium antimonide nanowires. They can be grown with a molecular beam epitaxy, and they can also be grown with chemical vapor deposition, things like that. Some of the methods I just want to throw out there. And so these are some bundles. And then here on the bottom right, we can see an isolated nanowire there. And to give you an idea of what this width is, it's about 30 to 50 nanometers. So in other words, it's about 300 to 500 atoms wide. See, we're playing with atoms here. This is very, very, very small stuff, and the thing these are just some really, really nice properties about them. It's got nice crystalline growth structure, and it's got a very large G factor, and that's one of the things that they wanted me to point out at the laboratory. So what's the interest with this nanowire? Well, as I mentioned, it's got a large G factor. It's got a high electron mobility rate. And we're going to do a comparison here in a moment, the next slide over, and it's got, as I mentioned, it's got a high quality growth structure. It's got some spin orbit coupling properties, so the relation between the spin of the electron as it rotates on its own axis and as it rotates and orbits around the nucleus of the atom there. And so these things can be measured with the quantum Hall effect. They can also be measured with the squid sensors, spin quantum interference devices, so squid detectors that we have there. And we can also harness those spin controls in order to manipulate in particular, how would you say it, modify the spins of these electrons to do some things that we want. Okay, and so that's what this is about. And we can see here on the left a nice comparison between indium antimonide and some other 3,5 materials. And so here on the far left we can see silicon, which is a commonly used semiconductor material in solid state research. And so we can grow nanowires using silicon, and we can see that it has an electron mobility rate of less than 1,000 square centimeters per volt seconds. And this is data pulled from materials that were measured and tested under 300 degrees Kelvin, or about say 80 degrees Fahrenheit, to give you a bit more of an idea. And so we can see everything highlighted in red here. So gallium arsenide, germanium, indium arsenide, these other compounds, and they have their different mobility rates. But we can see here on the far right, as I mentioned, indium antimonide has the highest mobility rate, electron mobility rate, that is, out of all these materials. And on the bottom, everything highlighted in purple, we can see that on the far left there's silicon. When we compare it to indium antimonide, it would be I don't know how you would say it, dirty. It's somewhat not as clean. Well, not somewhat, but we can say that it's not as clean as indium antimonide. So that's what we're looking here. We're looking at here is quality. So here we can see the project goal that we were doing in the laboratory. On the far left here, we can see a device where we planted where a nanowire is planted, and this with a certain recipe. If things aren't quite monitored correctly, or the recipe is not inputted properly, it creates these fractures here. You can see these cracks on the device where the where the components overlap with each other like that, and it can create problems within the research, and can delay things and whatnot. And so that's what we're trying to avoid, bad sample, and it's not what we want. But here on the right we can see a good example of a nanowire that's planted and placed, and on these with these cobalt contacts with proper HSQ planarization procedures, and reactive ion etching processes, so that everything contacts quite nicely, and we can get on with our research. So we're looking for less curvature at the top of this nanowire. And so this HSQ, we're going to get to that in a moment here. This is what we want. This HSQ is called hydrogen cell sesquioxane. So this HSQ is an etching. It's an etching resist material. That's what it is. And so here we can see a silicon we can see the silicon substrate on the left, this wafer, and then we have some spinner equipment. And what we do is we take a look at this HSQ dosage graph, the relation between the velocity of the spinner equipment and the thickness that we desire here. And so since we're aiming for about I'd say a thickness of about 110 nanometers. So while this is although mentioned in angstrom, this is measured in angstroms. 110, how would you say it, nanometers would be comparable with this 1108 angstrom thickness here. So we're going to input 3000 RPMs into our recipe here. And so here we can see a nice GIF image on the right that I've created for you that shows you what the HSQ planarization procedure does. This we apply the resist, then when it spins out, this resist material flattens out, pancakes out, which is nice to see. And then after that, it's baked and it's set in place. And then after that, then we take it over to the e-beam writer, the Vistec e-beam writer at the Nano Center, and that's done by Zedong there. And he writes some etching material onto this substrate. So once he does that, we can see these tiny little this tiny little row of these little dots on the left here on this wafer chip, this wafer substrate. And then we can use the P7 profilometer and the P6 profilometer in the laboratory to measure these little dots. And as you can see here, when we zoom in, these aren't actually little dots, but they're triangles. And these triangles they have these topological surfaces on top of this substrate layer, and we can see the height as depicted here on the right. And so these heights, we can measure them, and we can get an average. We can measure out some averages here, and we can see here that everything that's highlighted in yellow is our triangles. It's the material that was written by Zedong on the chip. And then we take it over to the reactive ion etching machines, or what we call the AV etcher. And so when that's done, we experiment with some PGS oxide recipes for about 2 minutes, because we're aiming for, let's say, since we're aiming for about 60 to 70 nanometers of this material, of these triangles. Well, that's what we're experimenting with. It's going to show us a difference before and after here. And so after applying this reactive ion etching procedure, we can see that we have a 16 nanometer difference between the changes of the height that's done after this procedure. And so since we're aiming for about 70-80 nanometers, originally this is well, 94 nanometers is close enough to what we want, because that's going to overlap just slightly with the applied nanowires that are going to be placed on the substrate. And so we have here some Profilometer scan data, and this is just to show you an example of what the data looks like before and after the reactive ion etching procedures done. And we can see here our future work. This is to stress the importance of planarization, and if things aren't done right, it can create cracks and problems. But this is the I guess you could say what we're experimenting with here is different heights that we're desiring for the chip, so that we can get on with our research in Majorana fermions, in the area of Majorana fermions, and how do you say it? Quantum computing. Okay, so that's that. And so ballistic transport, as I mentioned, that's just the it's similar to superconducting, because, well, we have superconducting. If you describe it in words, it's what happens when you have absolutely zero heat dissipation as we flow electrons from point A to point B. But ballistic transport is it's close to superconducting properties, but not necessarily superconducting. So there's some level of dissipation along the way, but it's near superconducting. Because if you have a material that flows electrons, the electron mobility from point A to point B, the how do you say it? If it's superconducting, it's gonna experience what's called the Meissner effect, and that Meissner effect is that transition from semiconducting or non-conducting into a superconductor. And so this ballistic transport is just saying that this electron mobility from point A to point B within this indium antimonide is going to be, it's not going to experience that Meissner effect on the other hand. And so that's what that's about. And we can use those properties therein to create devices that we can use for, what do you call it, antimatter. So that the whole fermion that those Majorana fermions that I mentioned is antimatter material that we're talking about. Okay, so I just thought I'd give you this quick talk here, and here we go. My video is finished. What are we? 13 minutes and 25 seconds. Whew. Alright, cheerio.